6.2 Properties of Parallelograms. In this lesson, we are going to look at the relationships between sides and angles of parallelograms and diagonals of parallelograms. They are going to have special properties. Now, some vocabulary for us. This is a definition here. The definition of a parallelogram is a quadrilateral. What does that mean? Has four sides. So a four-sided figure with both pairs of opposite sides parallel. So anytime you're told you have a parallelogram, you know you can say that opposite sides are parallel. And we know parallel does lots of good things for us. Okay, some more vocabulary for us here. Opposite sides do not share a vertex. So side BA and side CD do not have an angle in common. We can also add side BC and side AD. So those are our opposite sides. Opposite angles do not share a side. So if I'm talking about angle A here, well, angle A and B share a side, angle A and D share a side, but angle A and C do not share a side. And we can also put angle B and angle D are opposite angles here. All right, there's our vocabulary. Here's our first theorem. Now, none of these are named, but they are really easy to write, so it's no big deal on these. Some of these are shorter to write than some of the ones that we have that have actual names. So this says if a quadrilateral is a parallelogram. And what does a parallelogram mean? Opposite sides are parallel. So if we have a quadrilateral and opposite sides are parallel, so we have a parallelogram, then opposite sides are congruent. So if we have a parallelogram here, we can automatically come over and mark our opposite sides congruent. So we can just write that up here. I write parallelogram like this. Now, note here, you see the little symbol, parallelogram? You can use that, but you don't want to make it look like a square or just some random, quadrilateral. If you're really good at drawing them, you can use that as a parallelogram. I just write parallelogram, opposite sides are congruent. Now, this is a theorem, and the proof is actually really kind of neat here. So we're given that this is a parallelogram. Parallelogram ABCD. Notice you've got the little symbol there. It says parallelogram ABCD. Well, what does that tell us? That tells us that opposite sides are parallel. So we know that we can go in, mark that parallel and that parallel. All right, and then we've drawn a transversal here that cuts through our parallelogram. And why would we do that? Well, you know why. Alternate interior angles. We also have these alternate interior angles. So we've got parallel sides. That's just definition of parallelogram. We've got angle 1 is congruent to angle 4. and angle 2 is congruent to angle 3. That's alternate interior angles theorem. And what else do we have? We've got a line in the middle there. Color. So AC is congruent to CA. And I hate doing this every time. Symmetric property and reflexive property and symmetric property of congruence. And then what do we have? I see angle side angle postulate. Our triangles are congruent because of the angle side angle postulate. And that's going to let us make our sides congruent. Corresponding sides are congruent CPC TC. So I'll be able to say this side is congruent to this side is congruent to this side. So let's look at our proof here. We've got parallel lines, definition of parallelogram, right? Just definition of parallelogram. And then here's our alternate interior angles theorem. Our angles are congruent. There's our reflexive property. And then we've got our triangles are congruent by angle side angle postulate. And then we can say that we have congruent sides. Opposite sides are congruent. This is just our CPC/TC. So that's kind of a neat little proof there, using our triangles. All right, so that's two things we know about parallelograms now. All right, some more vocabulary for us here. Consecutive angles share a side. So A and D share a side. So we can add angle A and angle D share a side. Angle A and angle B share a side. Angle B and angle C share a side. Angle C and angle D share a side. So we have lots of consecutive angles here. So we have A and D, B and C. We can add angle A and angle B. And we can add angle C and angle D. So these are all consecutive angles. Notice we've got them here and we've got them here. Hopefully you're thinking, that goes with our parallel lines, and it most certainly does, because our next theorem says that if you have a parallelogram, quadrilateral, opposite sides, both pairs of opposite sides are parallel, consecutive angles are supplementary. So let's take a look at why this is. We know that those two lines, those two sides, opposite sides are parallel. And look, we've got a transversal here. And what do you see? I see same side interior angles, right? Purple's parallel. What about the other direction? We've got parallel sides there. Mark those parallel. They're cut by a transversal. What do you see there? I see same side interior angles again. We know same side interior angles are supplementary. So this should come as no surprise either, and it works for the right-hand side and the bottom as well. We can add in this transversal over here and this transversal up here, and we still have consecutive angles are supplementary, just like we saw up in our picture up there. Well, what do we do with this? We want to know what is the measure of angle P kind of hard to see over here. This is angle P over here. What's the measure of this angle if this is a parallelogram? Well, I know that these two angles are consecutive, so they're supplementary. So 64 plus the measure of angle P is going to equal 180. Just subtract 64 from both sides. The measure of angle P, 116 degrees. So I can say this angle measures 116 degrees. Well, guess what? Those on the right-hand side, those are consecutive as well, right? I can find the measure of this angle up here. What's it going to be? It's going to be 64 degrees. Guess what? These are consecutive as well. This angle is going to be 116 degrees. What does this look like to you? Have we seen, see if I can draw it kind of like this. We've seen this before, haven't we? With our dual sets of parallel lines. Well, this is going to lead us to our next theorem. This says if a quadrilateral is a parallelogram, opposite angles are congruent. And we just saw that in our picture, right? Look at our opposite angles are congruent. So parallelogram, opposite angles are congruent. Oh, we should go back. Where is it? Right there. Parallelogram, consecutive angles are supplementary. There we go. See, I told you, these names are, writing them out is almost shorter than some of the names we've had to write. All right, so we've got opposite angles are congruent. So if you have a quadrilateral and both pairs of opposite sides are parallel, your opposite angles are congruent. Now, this is a theorem, so again, it's proven. This one's kind of a neat one. We're given we have a parallelogram, so we know our sides are parallel. We want to prove that our opposite angles are congruent. Well, what do we have that lets us do that? I know that these are consecutive angles, right? Just by definition of consecutive angles. I know that these are consecutive angles, just by definition of consecutive angles. I know that these are consecutive angles, just by definition of consecutive angles. There's the first line of our proof there. I also know that A and B are supplementary because it's a parallelogram. B and C are supplementary. C and D are supplementary because it's a parallelogram, because consecutive angles are supplementary. So what can I say if A and B are supplementary and B and C are supplementary? What it has to be true? A has to be congruent to C because of our congruent supplements theorem. If two angles are supplementary to the same angle, in this case angle B, then those angles are congruent. And this also works for B and D for the very same reason. So that's a really easy little proof there. All right. I'll go through this proof with you. Need a little space to draw here. We are given parallelogram ABCD, and we know that segment AK is congruent to segment MK. So I am going to draw some stuff here. First, I'm going to draw my parallelogram. A, B, C, D. And we're working with a big triangle here. A, K, M. And we are told that this is a parallelogram. So we can mark our sides parallel. And we are told that segment AK is congruent to segment MK. Oh, I see things happening already. I'm going to make those two angles congruent. So angle A is congruent to angle M. Why do I get to say that? That's our isosceles triangle theorem. Okay, well, I've got an angle A. I'm going to mark it right there. What else can I say? I can say that angle A is congruent to angle C. Angle A is congruent to angle, well, we should probably call it BCD, because in our big triangle there's lots of possible C's. So BCD. And why is that true? Because in a parallelogram, opposite angles are congruent. And now, what do you see here? We are going to be able to say that angle BCD is congruent to angle, and they don't call it M. We shouldn't either. Angle CMD. And why do we get to do that? Our friend, transitive property of congruence. So, welcome back, proofs. That one was pretty easy. All right, that's 4 things now that we know about parallelograms. On to number 5, and this is the last one here. Lots of good stuff about parallelograms. If you have a parallelogram, your diagonals bisect each other. Bisect means we've got 2 congruent parts, and this means both of them get bisected. So not only are those congruent, but those are congruent as well. Point E is the midpoint of both of those segments. So that's actually really useful. How do we use that? Well, we are told, we're going to mark this as a good example. When you go, I don't know how to do this problem, I'm going to refer you to the good example. We are told that we have a parallelogram, so we can mark our diagonals congruent. We know that the diagonals bisect each other. This is going to allow us to write some equations. We've got x equals y plus 2 and y plus 10 equals 2x minus 8. We can't solve either of those directly, but we do know a value of x is y plus 2, and we can just substitute that right into there. So there's that happening right there. You can follow this example. It's just simple substitution, solve for your unknown. I think in the interest of time, we might skip this next one. We know we have a parallelogram, so those are congruent. Gives us 2 equations, y equals x plus 1 and 3y minus 7 equals 2x. I know a y, so I'm simply going to substitute in 3 times x plus 1. Don't forget minus 7, because I'm taking just this y right here. I'm putting that in for that y, don't forget your parentheses, equals 2x. Don't forget to distribute to everyone. 3x plus 3 minus 7 equals 2x. 3x minus 4 is 2x. Subtract 3x from both sides. Minus 4 equals a negative 1x. Don't forget your negative. Don't forget to get rid of it. So x equals 4. And then I simply substitute back in. Y equals 4 plus 1. So y equals 5. So 2 good examples for you there. All right. Our last theorem here is a little bit off the beaten path, and it looks like some stuff we've done before. This says if 3 or more parallel lines cut off congruent segments on a transversal. So let's look here. We've got 3 parallel lines, and one of our transversals has congruent segments. Okay, that's our requirement. What's the result? Then these 3 parallel lines cut off congruent segments on every transversal. So if I draw another transversal here, I know that those segments are congruent as well. And it doesn't matter how my lines are drawn. If I extend my parallel lines out here, I can draw a line through like this. Those are going to be congruent. I can draw straight up and down line. Those are going to be congruent. It doesn't matter. As soon as you know that your parallel lines are equidistant apart, then any other transversal you draw is going to be cut through like that. So let's do our last problem here. It says our lines are parallel. Okay, that's parallel to that, it's parallel to that, it's parallel to that. I have 3 or more parallel lines cut by 2 transversals, and I am told that the length of A, B, B, C, and C, D are all 2, 2, and 2. So these are congruent. That tells me that every other transversal is congruent. And I know that EF is 2.5 units long. So what is EH? Oh, that's the length of the whole thing. Well, I can just label all of these 2.5, add them all up, and we get 6.75. All right, and the last problem, we might as well just go on with this since we haven't paused yet. It says, what if EF, FG, GH, the length of those is all 6? So this is 6, 6, 6. What is the length of the length of AD is 15. Well, since those are all congruent, I know my top ones are congruent, and I can just do 15 divided by 3. All of those. Length of CD is 5 units. All of them are 5 units. Length of AB, length of BC, all of them are 5 units. All right, well, at this point, we need to get out our quadrilateral chart and start filling in some things. So quadrilateral means we have 4 sides. And what are we going to do with that quadrilateral? Well, we are going to give it 2 pairs of parallel sides. That makes a parallelogram. What do we know about parallelograms? Well, we know that the definition of parallelogram says that opposite sides are parallel. Both pairs of opposite sides are parallel. What else do we know? We know that opposite sides are congruent. We know that opposite angles are congruent. We know that consecutive angles are supplementary. And we know that the diagonals bisect each other. So that's some good stuff to add to our diagram here. Don't worry, we will get more. All right, that is our properties of parallelograms. Know these? Use these? They are your friends. Make sure you always have your quadrilateral chart here. It's going to be a big help. All right. Have fun with the homework. I really enjoy parallelograms. I hope you do as well.